Hi guys, so today we're going to go over question 3 on Form J of the AP Physics 1 test. So question 3, as always, it's an experimental design question with two parts. For the first part, we're given an experiment and a setup, and we're going to have to design an experiment to find something, and based on a linear graph. So this is the part where we're going to make the experiment. And then in the next part, we get a second experiment where you're given this setup, and they've already done the experiment. You're going to have to plot and make a graph, and you're going to scale the graph accordingly and use the slope or y-intercept to calculate your experimental value for the mass or whatever they're looking for. So in this case, we're going to come up with two ways to find the mass with two different setups to find an unknown mass. The first part is the first experiment where we're using a balancing system, so basically a torque setup, and a spring scale with a meter stick to find an unknown mass, the mass of a block, which is unknown. So we're going to try to make this unknown mass known somehow. So in part A and part B, you're going to make an experimental procedure. So I actually prefer to derive the equation for experiment first and then write out the procedure, because then you know what you're looking for and now you're going to use the lab to see how you measure it. So we know that torque is RF sine theta, and theta is always going to be 90 degrees because it's perpendicular in this setup. So we can simplify this to torque equals RF. And then R is going to be measured with this, and then a torque. The spring scale will always be at a fixed distance. We need to balance torques. So since we have 50 centimeters here, we have 0.5 F, and this is what the force that we're measuring from the spring scale equals RM0 G. And then we can change this to F equals M 2M0GR. So R, we can format like this: y equals mx, where y is our force, and then m here, and x. The slope will be 2m0g, and then x will be r. So using this, how are you going to design an experimental procedure? So we know what values we need to find. So all we need to do is show how to find them. Students will hang the mass, the block or mass, on the meter stick on one of the four holes provided. They will use the meter stick to determine the distance from the center or balancing point of the meter stick and record it. Then they will apply a force via a spring scale to balance the meter stick and record the force as read by the spring scale. These values will be combined to make a data point. Repeat this process 5 times to reduce experimental error or uncertainty, if you want to follow College Board's format, with the same distance from the balancing point used to hang the block or mass, and repeat the experiment across varying values of the distance the mass or block is from the balancing point. So this is a standard rotational experiment that you need to set up using torques. So we derived the equation here, and now we just have to explain it. Students should plot the spring scale readings or forces against the distance from the mass or block is hung from the center or balancing point. They will then use the slope of the line of the resulting best fit line to calculate an experimental value for m sub 0 using the relationship slope equals 2m sub 0 times g times g. So there you go. That's the first part. That's the design part. Now we're moving on to the analysis. We're given a completely different scenario where the meter stick's being used, and we're given the angle that the string makes with the meter stick and the tension force that's recorded by the spring scale. So here we have a table with the angles and forces. And the relationship, tension equals 5 mg over 6 sine theta. First, we're going to go to Desmos to do this part. And the reason we're doing this is because we're going to need a different scale here. And if you were to do this on the test, you're given these 1 over sine theta. So you would scale this from 1 to 0 to 3. And you're given the tension forces, so you would scale the vertical axis according to the label tension force, or FT, in newtons. And make sure you include units when you label the graphs, but that's for another story. So the x sub 1 would be 1 over sine theta. And for us, because that's given as horizontal axis, vertical axis would be tension force. Because the tension force would equal 5 mg over 6 sine theta. So we can just type it here, I guess. Ft equals 5 mg over 6 sine theta. And then we can say y equals m and x. So this would be y equals, and then from here, m equals 5 mg over 6. So then we can find m that way. So then we can go here and do 1 over sine. And this is the radians, so we have to do 22 pi over 180 for 22 degrees. And we can input the tension. We can input the values here of tension. Let's see. 2 variables defined in there. Wait, no. So let's fill in the table before we do the regression equation. So here we would do 21, 17, 13, 12, 8. And then we can do this thing where instead we're going to change the angle to what we need. 31, 36, 45, and 80. So we're getting a best fit line here. So we can do y1 equals ax1 equals, we can do a regression here, I'm guessing. So we can do a Desmos regression on here, and we get a best fit line here with a linear regression. So the slope from a linear regression we get here, on the real test you can do either the 2-point method, or you can state that you use Desmos or your calculator to do regression. So after you plot this graph, make sure you scale accordingly. So you would actually scale it differently and have 1 through 3 here, and the slope from 0 to 25. You would plot this from 0 to 25 so you could use at least half the space. But your graph should look like this. And I would say F tension force on vertical axis. And then part D, you're going to calculate the experimental value. So we will go back here and say from Desmos regression, slope of best fit line equals 7.9. And then we can do the slope thing over here and say 7.9 equals 5 mg over 6. And then 7.9 times 1.2 equals mg. And for using 10 for mg, we can say 7.9 times 1.2 times 0.1 equals m, and then m equals 0.948 kilogram. And if you did anything by hand or got different regression value, you could use the college rule will give you an acceptable range to do experimental design. So you should be good as long as you know what you're doing, but it's going to be a pretty tight range. But it should, and if you put like 0.8 something or 1.0 something, I think they will take that. They're going to create a range from which your value would be, but you have to demonstrate the graphing skills because they will require to do it. And yeah, Desmos is allowed on a test, so you can do the regression formula to get it. Just in case you want to know. So next time we're going over the final question on the test, which is the quantitative qualitative translation.